In the 1950s, scientists believed high-banked rivers throughout the eastern United States, a signature of the landscape, resulted from repeated floods which piled sediment onto the sides of rivers. Decades later, researchers Dorothy Meritz and Robert Walter presented a different theory for how these steep banks came to be: human activity. In 2008, they published a paper in Science suggesting that when Europeans arrived in the US 500 years ago, rivers on the East Coast were marshier and had far lower banks. To this day, their findings call into question the best way to spend the millions of dollars funneled towards improving rivers every year. Meritz and Walter's study began in the Little Conestoga Creek when a student showed Meritz a photo of 6-meter-high walls of sediment. Meritz doubted that floodwaters could have deposited enough silt to make a bank that tall. Her colleague, Robert Walter, agreed, and suggested that they might have formed from still, not moving water. It didn't take long for them to find the cause of the standing water, a dam downstream from the site. These mill dams were used to power flour and textile mills. After digging through historical maps and conducting fieldwork, they found mill dams were abundant throughout Pennsylvania. Further research also showed they cropped up in other parts of the eastern United States. Meritz and Walter concluded the thick banks were made up of legacy sediment, soil that eroded from the intense land transformation of colonial-era logging and farming. They were concerned that these large packages of sediment, still laden with pollutants, could negatively impact water quality as it eroded into the river channel. When too many nutrients, like phosphorus and nitrogen, end up in waterways, it can upset the delicate balance of ecosystems by causing massive algal blooms that gobble up oxygen. They believed restoration efforts that didn't address legacy sediment could run into problems with pollution down the road. Not all researchers agreed with their conclusions. Some pointed to areas without dams with lots of legacy sediment, while others argued that the old 1950s framework still stood true. Amidst all the debate, state and federal agencies weren't sure how to account for legacy sediment in future projects. The duo decided to apply their findings on a smaller scale, a tributary of the Little Conestoga Creek, which borders the sprawling farm fields of Lancaster, Pennsylvania. In 2011, over 22,000 tons of legacy sediment were removed from the banks of Big Spring Run, transforming the steep, meandering river to a braided, gently sloping system. Today, Big Spring Run is almost unrecognizable. Wetlands have emerged and native species of animals and plants flourish. The wetlands soak in floodwaters, while the vegetation helps hold sediment in place, preventing large amounts from moving downriver. A report published this year shows just how effective this rehabilitation was. 85% less sediment and 79% less phosphorus make their way downstream. Removing thousands of tons of sediment is costly up front, about $1,150 per 1 meter of stream length. But it's far more effective at reducing sediment and nutrient pollution than other, more well-known management practices, like planting vegetation on the banks of rivers to filter sediment before it enters the water. Its success has spurred similar projects, and more are underway. As the Chesapeake Bay, the estuary that Big Spring Run feeds into, grapples with how to reduce incoming nutrient and sediment loads, the contributions of legacy sediment are still unsettled. Continuing to understand how humans have transformed landscapes will be vital to ensuring that the money and time invested in resculpting rivers is ultimately helping, not harming the environment.